it is good. Most of you have understood 01 knapsack problem and backtracking algorithm to solve it. And also most of you understood concept of bound function. But still some of the students are having doubt on bound function. So before starting the next topic, I am explaining the purpose of bound function again. Okay, so now just first see what is knapsack problem. Okay, so here to understand the bound function, see knapsack problem. Okay, so knapsack problems are in two flavor. One is what? Fractional knapsack, or you can say that the fractions are allowed. Okay, fractions are allowed, and the second is fractions are not allowed. Okay, see, the knapsack problem are of two types. One, when the fractions are allowed, and when the fractions are not allowed. So in the knapsack problem, when fractions are allowed, that problem is called simple knapsack problem, or simply the fractional knapsack problem. Okay, so simply if we say that the knapsack problem means fractions are allowed. When fractions are not allowed, it means that problem is simply 01 knapsack problem. Okay, so first clearly understand that the one is fractional, where the one knapsack problem where fractions are allowed. The second one is where the fractions are not allowed. Number of students are having doubt that this is a greedy method, this is a backtracking. These are the technique to solve the knapsack problem. Simply it doesn't mean that fractional knapsack is somehow related to the greedy technique. Greedy technique is one of the problem solving technique to solve fractional knapsack problem. This fractional knapsack is not related to greedy technique anywhere. This is the problem. Greedy technique is a method to solve fractional knapsack. Okay, the same 01 knapsack problem cannot be solved using greedy technique, so we go for other solution, like other problem solving technique, like backtracking, what I explained. Next is branch and bound. So branch and bound and dynamic programming. There are two more technique by which we can solve this 01 knapsack problem. Okay, now see what happened in fractions, simple knapsack where fractions are allowed. In both the problem, the objective is same. The highest profit is achieved. Okay, in the fractional knapsack, when we solve the fractional knapsack, important note that the profit earned is always maximum. When the fractions are allowed, then the profit earned is always maximum. What is the meaning of that? If suppose we are solving a knapsack problem where the fractions are allowed and what we get the profit, that is the maximum, and when the fractions are not allowed, means it is the 01 knapsack problem, then profit may not be maximum. Okay, now you can see, you can check in the 01 knapsack problem part 1, I have given two examples, and you can check that the profit is maximum only when fractions are allowed. This is the problem what I have given in the assignment. You can check the same. What I said, that the maximum profit is achieved when fractions are allowed. Okay, so here see, if suppose this is the knapsack instance or example. And here, if fractions are allowed, first understand, there I am not talking about the greedy. Number of students are taking the term like greedy technique or backtracking. Just forget about the greedy and backtracking. Simply concern about that whether fractions are allowed or fractions are not allowed. So here first I am considering this flavor, this type of problem, simply to solve this knapsack instance when fractions are allowed. So when the fractions are allowed, then simply at first we arrange, you know that the objects according to the decreasing order of profit per unit weight, which is already given. Okay, and now when fractions are allowed, we know that the problem is solved by greedy technique. So when we apply the greedy technique to solve this problem, first we arrange the objects according to the decreasing order of profit per unit weight, which is already arranged. Here profit and per unit weight, so you can compute profit per unit weight is what? 9, 7 and 6.6. Okay. So here the profit and weight vectors are arranged. Now if we solve this problem when the fractions are allowed using greedy technique, then x1 equal to 1 as the m is 14 and the weight is what? 4. x2, second object, is also can accommodate into the knapsack, so simply 6. So now at this point the total weight is 10 and the knapsack capacity is 14. So the next weight cannot accommodate on the knapsack as the remaining capacity is 4. So simply x3 equal to 4 by 5. Okay. So if fractions are allowed, again note down that this is the solution vector. Here the solution vector is what? 1, 1, 4 by 5 and 0, 0. 1, 2, 3, 4, 5. So this is the solution vector when the fractions are allowed and I solved this problem using greedy technique. Now compute its profit. So when we compute its profit, the total profit, this weight is the whole. So simply the 44 plus 60 and the third weight, the 4 by 5 into 45. Okay. So 44 plus 60 plus 36. 4 by 5, 14 and 4 by 5, yes, 36. So 140. See, this is the total profit earned or achieved when the fractions are allowed, and knapsack is 100% full, because whatever with the remaining capacity we take the fraction of the last object which is not fit. Okay, now here this is the profit and all of you have solved this problem using 0-1 knapsack. Okay, 0-1 knapsack means when the fractions are not allowed. So see, this is the solution when fractions are allowed. Fractions are allowed. Okay. So for any instance, if the fractions are allowed, then the profit, I said that the profit achieved is maximum. Okay. So here, when the fractions are not allowed, when fractions are not allowed, okay, in both the cases our objective is to find the optimal solution. So in the case fractions are allowed, this is the optimal solution. In the case fractions are not allowed, as you saw, many of you have solved this example, almost all, because all of you have submitted the assignment. So its solution is what? The solution vector is 0, 1, 1, 0, 1. Okay. So here simply 6, 5 and 3. So the total profit, if we compute here, in this case total profit is first weight is completed and 60, second weight sorry 60, and the third weight is 45, fourth weight is excluded, and fifth object is included fully, that is 20. So the total profit here is 125. See what I am saying that पहले सबसे पहले आप ये अच्छे से समझ लो तो आपको आगे कभी भी प्रॉब्लम नहीं आएगी कि when in the knapsack problem, if fractions are allowed, then the profit achieved is always maximum. Profit achieved is always greater than or equal to the profit achieved when fractions are not allowed. Okay, so here when the fractions, for the same example, when the fractions are allowed, the total profit is 140, and when the fractions are not allowed, the total profit is 125 for the optimal solution. So when the fractions are allowed, the optimal solution is this one, and when the fractions are not allowed, that is 0-1 knapsack problem, the optimal solution is this. Okay, so just note down always that, because this is the main essence of this backtracking algorithm or bound function, ki why in bound function we allowed fractions. Okay, now see the bound function. Here the many of students have understood, but few students are still having doubt on bound function. So in bound function, first understand why I am using bound function, because here I do not want to explore whole tree on the right branch. So we want some bound function, some upper bound, so that we can kill the node without moving downward. Okay, so here when the bound function is called, first bound function is called only for right branch when the kth object is excluded. So when the kth object is excluded, it means I have already taken the decision for 1 to k minus 1 object. So simply just say x1, x2, so on, xk minus 1. The decision for k minus 1 objects have already been taken. Some of the xi's are 0, some of the xi's are 1. And here xk is 0, xk is removed, and then xk plus 1 to what? Xn. See, so just I don't have any we do not have any type of restrictions on this, because these objects, the decision for this object have already been taken, and the kth object. Now the remaining objects are what? K plus 1 to n, and some solution vector have already been generated, because this is a problem to find the optimal solution. So what solution have already been generated? Their profit is stored in F. F is the profit for the solution generated so far. Okay, now here see, this is the bound function. First clearly note down that this bound function is in the changes, also note down the changes in the last backtracking part 4. Just here you have to declare the profit as float. Simply the reason is that this is returning the fractions, and if this part as M, C and W are integer. So if you implement this algorithm on C language, then this will return what? The integer part. So here it is required that you have to convert it into real. Otherwise it will truncate the fractional part and it may not give the maximum profit. Okay. So see, first what I said that just when fractions are allowed, I will always get the maximum profit. So I have already taken the decision for k minus 1 object. Kth object is removed or excluded. Now I am having the remaining objects k plus 1 to n. Okay. So here I have to take the decision for k plus 1. See here, just in the bound function, this is the bound function. In the bound function, just k plus 1 to n. For the remaining object, I relax the condition. Condition means fractions are allowed. For what? For k plus 1 to n. The fractions are allowed and we compute the profit according to the greedy method. Just by solving the problem using greedy method for relaxing the condition for the object from 0, 1 to fractions. Here for k plus 1 to n objects, fractions are allowed. And what profit is achieved? This. Simply just we add this profit and CP is the profit of this. And when the function is called, CP is this profit, and simply just whether the k plus 1th object can be included fully or not, and whatever be the last object which is not fitted, just we take its fraction. What I do in greedy technique when fractions are allowed, and then what profit is generated, this is written. So this is the total profit B here in the bound function B. So B is here float, so the return type of the bound function is float, as well as the f variable. There are only one change in the main function, just you declare f also float, because float or real means f is f may be in fraction. Okay. So now I think just you understand the concept of bound function, but I try to explain it with state space tree, so that because in other technique like the next technique branch and bound, the same bound function is used. So I want that carefully you understand the concept of bound function. One thing, और कहीं पे भी आपको ये मेंशन नहीं करना है कि बाउंड में ग्रेडी यूज हो रहा है. नो, बाउंड में ग्रेडी नहीं यूज हो रहा है, बाउंड फंक्शन में फ्रैक्शंस अलाउ कर रहे हैं. Just carefully note down that in the bound function for k plus 1 to nth object, fractions are allowed, and when fractions are allowed, then greedy method is used to solve or to compute profit, and whatever the profit generated from this bound function is maximum profit, what I explained. Okay, so here if we consider the state space tree for this algorithm, so here see W I am writing here, W is 4, 6, 5, 2, 3, and the profit is 44, 60, 45, 14 and 20. Okay, so first node is, I said that I have drawn part of state space tree for this example where the solution vector generated so far is 1, 1, 0, 0, 1 and the profit is 124. Now I will explain whether to move in this direction or not, in downward direction. For this purpose, for the right branch, when the first weight is excluded, see just here you can see carefully that this subtree, when the first object is included, is explored fully. Now the right branch tells that the first object I am going to exclude. So if the first object is excluded, then whether we will get solution which is better than the solution vector whose profit is greater than the profit of the solution vector generated so far. Okay, so now for this, the bound function for the right branch, this bound function is called. So here for this bound function, k is here what? K is 1 as the first object is removed. B is 0, the current profit, and C is the current weight. No weight is included till now and no profit is earned. So now this loop, the I simply run from k plus 1, that is 2 to 5. So here I equal to, first I equal to 2. I is 2, C plus Wi. C is what? 0, and 0 plus W2. W2 is 6. So 0 plus 6 is less than 14. So here the second weight can be included. So updated weight in the knapsack is 0 plus 6 equal to 6. And then updated profit is 0 plus the profit of the second weight, that is 60. Now I will be 3. This condition is true. C and B will be updated, and thus again the loop will execute. I equal to 3. So W3, here W3 is 5. So 6 plus 5 is less than or equal to 11, that is less than or equal to 14. So again C will be updated. C is 6 plus 5, 11, and the profit earned is 60 plus the profit of the third object. Profit of the third object is 45. 5 and 10, that is 105. Okay. Now the I equal to 4. I equal to 4 and W4 is 14. Sorry, 2. W4 is 2. So 11 plus 2. So 11 plus 2 is 13. Again, this is less than or equal to 14. So here we can add C equal to 6, that is 11. 11 plus 2 equal to 13, and B equal to 105 plus 14. 105 plus 14, 9, 119. Okay. Now see here, till now the value of C is 13 and B is 19. The value of I is here 5. Fifth weight. When I am considering the fifth weight is 3 and the current weight is 13. C is 13. 13 plus 3, 16. So this condition is false. Now this condition is false, then the else part will be executed. It means now the fraction of the fifth weight to be considered, and carefully see the fraction. The remaining capacity here 13 and the capacity of the knapsack is 14. So the remaining capacity B is what? 119, and we take the fraction M minus C. 14 minus 13, that is 1. 1 by 3 into Pi. Pi is here what? P5, that is 20. See, if suppose I previously in the part 4 I have not typecasted this expression. Okay, now see, if we execute this statement as it is, then 1 by 3, first 1 by 3 is executed and both are integer. M is integer, C is integer, M minus C according to the priority, first division to be executed, then only the multiplication to be performed, whatever. So here M, C and W all are integers. So 1 by 3 will return 0. 1 by 3 will return 0. So the value of this is 0. And here the profit returned, in this case bound function 119, which is less than what? Which is less than 124. Which is less than 124, so node is killed. So the algorithm will not work correctly, and it will generate, if you do not typecast there, then 11001 is the solution, and it will generate this solution whose profit is 124. So here, because fractions are allowed, so first we have to consider 1 by 3. So here the typecasting is required so that its value is some 6.6, and simply this is 125.6. Now see what I did. Simply from the third weight to fifth weight, I am checking one by one if the weight can be added. It is not exceeding from the capacity, then we include it fully. And the last weight which is not fitted, simply we take fractions. So here what I am doing it, for the right branch from k plus 1 to n, fractions are allowed, and we solve problem using greedy method and calculate the profit, this profit. And if this profit is greater than the profit profit of the solution vector generated so far, it means that this we can move to the right branch. Otherwise, see, just like here, if why I kill this node, if suppose the fractions are allowed from this, suppose at this point from 3 to 5 fractions are allowed, and the bound function is called to move in this direction or not, the profit returned by the bound function is less than 124. Suppose if the bound function is less than 124, it means that the profit returned when the fractions are allowed is less than, it means we will not get the better solution on moving downward direction. As I said, if the fractions are allowed, then I will always get the maximum profit. So in this way we move in this direction, and now you can complete it, and I think you understand the concept of bound function. Only changes here that just you have to make the profit in the in the backtracking part 01 knapsack problem part 4, to make B as float, return type bound as float. Here the typecasting is required, and simply in the main, before the main, F should be declared as float. Thank you, and the next lecture I will explain branch and bound technique. Thank you.